Electromagnetic induction. In this figure, you can see two poles of a magnet, and in between two poles we have a wire AB, and the two ends of this wire are connected to a centered zero galvanometer. Galvanometer is a sensitive device. It is used to detect electric current. Let me discuss this figure first. We can say magnetic field lines are going from north to south in between the two poles, and if we move this wire up and down vertically like this, then we observe deflection in this galvanometer. And the reason for this deflection is, while you're moving up and down, you will cut magnetic field lines, and this produces change in magnetic flux, which induce EMF, and this EMF is producing electric current in the wire, which we are detecting through this galvanometer. In above figure, a straight wire AB is placed in the magnetic field between the poles of a magnet. The ends of AB are connected to a galvanometer. When AB is moved vertically, the needle of the galvanometer shows a deflection. Why there is a deflection? Because a current is induced in the wire, and this effect is called electromagnetic induction. Let me point out that galvanometer is a very sensitive device. It is used for detecting small currents. An EMF is induced because by moving the wire vertically, the magnetic field lines are cut, and this causes change in magnetic flux. There are three ways by which you can increase the size of deflection. Number one, you can take a stronger magnet if you want to increase the strength of current in this galvanometer. You can take stronger magnet and you can move this coil faster perpendicular to the direction of magnetic field, and also you can increase the length of wire AB. So there are three ways by which you can increase the size of deflection in this galvanometer. The same thing I have written in my notes. There are three factors that affect the size of the deflection. Number one, strength of magnetic field. Stronger magnet give a greater current, more induced EMF. Speed of movement of wire. Faster movement give greater current. Another factor is length of wire. Longer length of AB give greater EMF and greater current. An EMF is not induced when the wire is held stationary between the two poles of magnet. So when the wire is stationary, no magnetic field lines are cut and there is no change in magnetic flux. So there will be no EMF in the coil. You can consider another example. Here you can see a coil, a copper coil. This copper coil is called solenoid, and if you move this permanent magnet in this direction, then you will observe deflection in the galvanometer. And the reason is that when you are moving the magnet toward the coil, the magnetic field lines are cut. Like you can imagine magnetic field lines going from north to south. So these magnetic field lines are also passing through the coil. So when you move in this direction, when you move the magnet in this direction on left hand side, you will see magnetic field lines passing through the coil are getting cut. So this creates change in magnetic flux, and this change in magnetic flux induce EMF. So this is another way of observing the same phenomena. Let me read it for you. Above figure shows a permanent bar magnet next to the circuit that contain a coil and a galvanometer. When the magnet is moved to left and inserted a small distance into the coil, the galvanometer shows that there is a current in the coil. Because magnetic field lines are cut, which produce change in magnetic flux, and therefore EMF is produced or induced. There are two laws which are relevant in this topic. First is Faraday's law of electromagnetic induction. This says that the induced EMF is directly proportional to the rate of change of magnetic flux linking the coil. Now, if this is very clear, when you increase the rate of change of flux, magnetic flux linking the coil, then you get greater induced EMF, and this means greater current in the coil. The second is Lenz's law. It says the direction of the induced EMF is always in such a way or in such a direction so as to produce effect to oppose the change that is causing it. Now let me explain Lenz's law to you. I will consider the same situation, and let me move this magnet to my left, and the Lenz's law says that the direction of induced EMF or the direction of current is in such a way so as to oppose change producing it. Now, how this coil can produce change, or how this coil can produce opposition to the change? It is possible when you are moving in this direction to the left, then this end of the coil become north. So when it happens, you will see that this north and north will repel each other, because we know like poles repel. And if you want to check the polarity of Q, you will see that this end Q will be north in order to oppose the motion of permanent magnet to the left. I can also put it this way, that if I am moving this permanent magnet away from the coil, that is to the right, then this end will become south to oppose the change. Now this coil will attract this permanent magnet, and once again it is opposing the change. So when this end becomes south and this end becomes north, then the polarity or the direction of current will be changed, and your galvanometer will diffract in opposite direction. The following factors affect the magnitude of the deflection of the galvanometer. Number one, number of turns in solenoid. If you increase the number of turns in this solenoid, then you will get greater deflection and you will get greater current. The second is speed with which the magnet enters the coil. So let me go back to my previous position. Initially I said that this permanent magnet is moving toward left, and to oppose this motion, this end become north, because like poles repel each other, so there is an opposition according to Lenz's law. So if you want to get more current, you have to move this permanent magnet faster toward the coil. So this is my second point, the speed with which the magnet enters the coil. Greater the speed, greater the value of current, greater will be the induced EMF. The third is strength of magnet. If you take stronger magnet, then you will get greater current, and this can be detected using this galvanometer. Deflection of the galvanometer gets reversed if we withdraw north pole of the magnet from NQ. I've already shown this. And if you stop moving the magnet, then the induced EMF becomes zero, because in this case no magnetic field lines are cut.